I would like to start my presentation with this picture. This is Borgenstave Church. It's around 200 kilometers north of Oslo in Norway. It's entirely made out of wood, and it has been standing perfectly preserved for almost 900 years. And the reason for this is that wood is able of such durability, as well as possess characteristics such as lightweight and high strength. They make a very appealing material for material science. Furthermore, the structure of wood itself, it has been optimized by nature for more than 270 million years. This is a period definitely longer than a PhD, and tells us that there is a level of very careful design in nature materials that we're still struggling to achieve with synthetic man-made materials. Furthermore, the the need for material is expected to increase. We will hit almost 10 billion people in the next 30 years, more or less, and we will expect to ask for material that are, of course, performing and innovative, but it will be more and more important for them also to be cheap and sustainable. And in this sense, forests can actually present a resource, and while they will not solve all issues regarding climate change, they still present an alternative to the common use fossil-based materials. And forests are able to store carbon dioxide, and they are self-replenishing. Furthermore, the orthotropic and finely tuned structure of wood can present design opportunities for novel materials. More in detail, in material science, they can actually fill a gap that is currently present. And more specifically, we have become better and better in building materials from the molecular as well as the nanoscale up to higher level materials. However, we're still struggling in achieving a high level of hierarchy, as well in translating the good mechanical properties that we have at the microscale up to application-suitable dimensions. So it's quite appealing to think if we can actually skip this bottom-up assembly and instead use materials that have already been optimized from the molecular up to the macro scale. Furthermore, wood itself presents characteristics that are particularly appealing in material science. And this is the combination of both lightweight as well as high strength. Furthermore, wood tissue is very oriented towards the growth direction of the tree. And it means that we can actually use this orientation, for example, for conductance, thermal conductance or electric conductance, as well as anisotropic optical properties. Furthermore, wood has a lot of porosity, both at nano and at microscale, which means that there is space for us, for example, to introduce functional moieties inside the structure that has already been optimized. In this sense, I should open a parenthesis on the structure of wood, as you might be familiar with how the wood looks at the microstructure. However, unless you've used the microscope, then you don't know how wood looks at the microscale. It can be described in simple terms as an array of hollow tubes very densely packed to each other. And these hollow tubes are wood fibers, which are basically wood cells that have differentiated, matured, and then they have died. Since they are dead, actually the inside of this space, called the lumen space, is empty. And this is what provides most of the porosity inside the wood structure. These fibers are connected, glued, we can say, to each other with what is called the compound mid-lamella, which is the first layer that is deposited during cell differentiation. And at the same time, they're able to communicate with each other through very small canals that are called pits, so that it's possible both for water and nutrients to flow and be exchanged between the wood fibers. At the nanoscale, the structure of wood can be described as a fiber-reinforced composite with the cellulose microfibrils, which provide the strength and stiffness, immersed in a matrix of hemicellulose and lignin. So as I said, wood actually sounds very appealing for material science. However, working with it is not necessarily an easy task. It actually comes with challenges, and the most important of which is heterogeneity. So the structure I just showed you, as well as the component I've talked about, can change even to a great extent between different wood species, between different individuals, even between different tissues in the same individual. And the reason for this is that wood actually responds to external stimuli. It needs to be able to adapt to the environment. Furthermore, it's accessibility. I've talked a lot about the porosity present in wood. However, this porosity is not necessarily accessible all the time. And actually, after we harvest the wood, a drying process starts, which actually close, in most of the cases, the pits, which are the communication canal between the fibers, which means that in most of the cases, it becomes very challenging if we want to introduce external moieties in the structure. Finally, and this is a common problem in material science, is to achieve a good balance between modifying the structure for our purposes, while at the same time preserving the well-optimized native structure of wood, in this case, as much as possible. In this case, the possible solutions are, in the first case, to develop modifications that are as universal as possible, meaning that we should expect similar results if we're working with different tissues or with different wood species. Secondly, what we can do is to increase the surface area, to increase the possible pathways for the introduction of functional moieties, or for instance, to open again the pits between the fibers. And finally, to try to preserve the well-optimized wood structure, we can try to use treatments that are as mild as possible to preserve both the native components as well as the structure. More in details, the objective of my thesis can be divided in 3 points. The first of which is to develop top-down methodologies for the modification of the wood structure. And again, these methodologies aim to be as mild as possible, both on the structure and on the wood components. Secondly, is to see how this modification actually affect the wood structure and how this in turn affects the properties of the material. And finally, to demonstrate how this functional wood, the modified materials, can actually be used for functional materials or for novel applications that go beyond the one traditionally used for wood. So both my thesis and this presentation will focus on 2 main applications. So the wood structural tailoring will be focusing either on the densification of thin wood specimen to obtain structural and optical materials, or to tune the wood structure so that we can achieve wood polymer composite for energy application. In the first category, we have a first approach which focuses on delignification and cross-linking of thin wood specimen, while in the second approach, we try to not delignify, but instead to modify lignin inside the material, still to obtain thin wood films. In the second category, we have composite with prepolymerized pPSS, with in-situ polymerized polypyrrole, and finally, a wood foam of high conductivity as well as compressibility. So first focusing on the first category. What has been done so far for the purpose of densification is that if we actually increase the density of the material, we expect the mechanical properties to improve. And the current approaches are mostly of 2 types. So either bottom-up approaches, which means that we first need to liberate fibers or microfibrils from wood structure, and then again build structure that are normally isotropic. However, the liberation of these fibers or microfibrils actually are energy expensive, and in most of the cases actually damage the fibers themselves, which means that in the end we will have materials with less optimal mechanical properties. Alternatively, we can directly densify thin wood specimen, and this has been done in literature mostly on hardwood, majority of case on balsa wood. And this again requires extensive removal of component, mostly lignin and hemicellulose, so that the material can be more compliant to densification. However, this normally leaves just a cellulose scaffold, which means that it is usually moisture sensitive as well as shows low durability. So in our case, we focused again on a top-down approach on thin wood films. And what we wanted to do was instead to work on softwood and to try to preserve the components as much as possible. At the same time, we did need to modify the structure. So in this case, the structural tailoring need to find a balance between increasing the compliance so that the material could be easily densified, while at the same time maintaining the alignment of the wood fiber, so to not disrupt the orientation, so that uniaxial mechanical properties can actually be improved. In the first approach, to increase compliance, what we wanted to do was to remove lignin from the wood structure. However, especially softwood can be very sensitive to extensive delignification. And the reason for this is that the more we remove lignin, which is in the millilamellar region, which is a lignin-rich area, then we progressively actually remove the glue that is keeping the fibers together. So if we push the lignification too much, the structure will tend to fall apart. So to prevent this, what we did was a cross-linking with butanediol diglydicylator, which is a common cross-linker used for polysaccharide. And what it does, it attaches to the OH groups in wood and prevents the loss of cohesion when we remove all the lignin from the structure. So the materials were prepared to 3 steps. So we have first the BDDE cross-linking. This was followed by peracetic acid delignification. And the reason for this is that we wanted the slightly milder delignification method so that we could preserve as much as possible of the hemicellulosic content. Finally, then this material is densified at high pressure and high temperature. So first of all, we can see what happens when we cross-link the material. This is the microstructure of native wood. So you can see the cellular arrangement as well as a very dense middle lamella. If we delignify the material without first improving the cohesion, what happens is that the fibers are barely holding together, and we can see that the middle lamella region looks almost completely eroded. This means that this material tends to fall apart into individual fibers. Instead, what we achieve if we first cross-link the material is actually a better preservation of the cellular structure. Of course, it does look softer, and this is because we are still removing lignin. But anyway, the cellular structure is preserved, and the middle lamellar region is still maintaining the cohesion between the fibers. These materials were then used in the first case. We took the fibers, we used filtration setup, so with common paper-making method, and we made the film. While in the second case, we just used the material that kept its alignment then for the densification step. What happens after densification? First, in the first case, with the random in plane hollow fiber film, we can see that the material presents random in plane fibers from the surface, and then from the cross-section, then we can see that there are a lot of gaps inside the structure, which tells us that the packing is not very efficient. Instead, if we press the material that kept its original alignment, then we can see that even if the material is slightly thicker, then its packing is much more efficient and the obtained structure is much more dense. At the same time, we're also preserving the alignment of the fibers. This translates in different optical properties. In the case of the anisotropic materials, then what we can see when we shine a laser to the structure, that the light will be scattered in an orthogonal direction compared to the fiber direction. So what we will see is basically an ellipse shape on the horizontal direction. So the light would be preferentially be scattered on the horizontal and not in the vertical. Instead, if we do the same thing with the isotropic paper, then we will see that there is no preferential light scattering. So both horizontal and vertical are to the same amount. Regarding the transmittance, we could also see that the aligned veneer, even if it's slightly thicker, it still shows much higher transmittance compared to the hollow fiber film. And the reason for this is that it had a lot less gap inside the structure so that the scattering within the material could be minimized. Regarding the mechanical properties, we could see a similar behavior, meaning that the aligned material showed much higher both tensile strength as well as Young's modulus compared to the random in plane film. And the reason for this we can see from how the material actually fractures. In the first case, in the aligned material, we can see that the fracture itself happens within the fibers, and this requires much higher energy compared to the random in plane film. Here we see a lot of fiber pull out, which means that the mechanism is basically failure at interface between the different fibers. This requires a lot less energy, and it translates in lower Young modulus as well as tensile strength. So we've seen in this case how to achieve thin films, actually preserving the alignment can be beneficial both from an optical and a mechanical perspective. However, we did need to delignify the material. So then we wonder, can we actually keep the lignin inside? So in this case, what we wanted to do was to modify lignin, so only partially delignify the material, so that the cohesion between the fiber could be better preserved. In this case, we use sulfonation, so we simplified the process with only one step, and this was followed by, again, densification. Here we needed to go at a slightly higher temperature, and the reason for this is that we wanted to go above the glass anesthesion temperature of lignin, which in this case it was around 127 degrees. The reason for this is that we wanted to mobilize the lignin within the structure so that it could act as a binder for the whole structure. So first we can see what happens with sulfonation. And keep this in mind because this will be a common procedure also for the second part, so for the wood and conducting polymer composite. So what happens when we push sulfonation is that we have a progressive erosion of the mid-lamellar region, which is lignin-rich. However, even if we push sulfonation for 14 hours and we see a lot of erosion in the mid-lamella, still the cellular structure of wood is not undermined. We could also see that there is a progressive decrease in lignin content from the around 29 native wood percentage down to 15%. So in any case, we're still keeping inside the structure at least half of the native lignin content. In a similar way, we could also see the increase of the surface area as we're creating more porosity and empty spaces inside the wood structure. From a chemical point of view, we could see an increase of charge groups. In this case, is sulfonic groups, up to around 350 micromole per gram, the longer we push the sulfonation step. So what happens if we densify these materials? We can see from the macro scale that there is a progressive improvement in the appearance of the film. And this is also confirmed by the cross-section, where we can see a progressive diminishing of the amount of gaps and fractures inside the wood film. And at the same time, we were achieving smoother and smoother surfaces. However, if we push the sulfonation for too long, then we can see cracks appearing again both at the macro as well as the micro scale. And the reason for this is that lignin that remains in the structure is not sufficient enough to act as a binder for the whole material. The optical properties of this material, we could see that there is a progressive improvement of the transmittance the more we push sulfonation. So the materials that are both 5 hours and 14 hours show the highest transmittance. And this is a joint combination of fewer gaps as well as thinner films. At the same time, all of these materials present UV blocking, and the reason for this is that the functional group in lignin can actually absorb part of the UV spectrum. A similar trend we could also see from the mechanical properties, which means that we have an increase of both Young modulus as well as tensile strength the more we push sulfonation time. However, if we push sulfonation too much, so 13-hour and the green line, then we see again a decrease in both tensile strength as well as Young modulus. So we can see that there is an optimum level both of sulfonation as well as lignin content. Furthermore, as we are preserving the lignin, then we could also see some additional properties. First of which is improved moisture stability. So if we look at the sulfonated densified sample, so the pink line, then we can see that a drop that is deposited on the surface actually can stay stable up to more than 10 minutes. Instead, if we do the same thing with the native densified wood, then the drops disappear completely. And this comes actually not really from the chemistry, but from the morphology of the sample. So we increase the density, which means that in the end it will be more difficult for the water to seep through the surface. When the chemistry actually comes into place is for recyclability, because we have introduced a lot of sulfonic groups in the structure that repel each other. So if we then submerge the film in water and we leave it soaking for around 1 hour, then it's possible to easily fibrillate the sample. In this case, it was done just with a common kitchen blender. And the fibers are well preserved and can be used for further purposes. In our case, we demonstrated the possibility of making an isotropic film, where we could see the fiber being used for fiber reinforcement, for example, in composite, as well as being put back into the pulp and paper streams. So to summarize this section, we've seen how thin films can be obtained through 2 different methods. The first one was achieved through delignification but it was necessary to preventively cross-link the material. And this can be seen actually as a more universal strategy to use softwood, the lignified softwood, in wood nanomaterials. The other thing is that we could also see how preserving the alignment is beneficial both from an optical as well as a mechanical perspective. In the second part, we see that if we preserve lignin, then it's important to tune the level of sulfonation as well as lignin content. And that preserving the lignin also endows the film with additional properties. In this case, it was UV shielding, moisture stability, as well as recyclability of the material. So we've seen how to tune wood structure towards densification and optical and structural material. We also try to tune the wood structure so that the interaction with the polymer could be improved for the use in energy application. Wood has already been used in energy application, and the reason for this is that it possesses multi-phase transport, which means that there are a lot of low tortuosity channels inside the wood, which are the lumen space. And this can be used for the conduction of ions. However, how you're probably familiar with it, wood is electrical, non-conductive. So to impart electrical conductivity, what has been done in literature is focusing mostly on either carbonization. However, in this case, what is obtained is a very brittle scaffold. Otherwise, if the structure wants to be preserved better, then the possibility is to infiltrate conducting moieties. Most of the cases are either metal, metal oxides, as well as conducting polymers. However, in this case, again, extensive delignification to open up the structure is necessary, which means that the wood is just used as a passive substrate to hold the polymer or the metal, but is not actively participating in the electrochemical properties. So what we focused on in our case was wood polymer composite, but what we wanted to do was, of course, increase accessibility so that the material could flow better inside the wood structure. But at the same time, we wanted to improve the electrostatic interaction, attraction actually, between the wood and the polymer, because we wanted wood not to be just a passive substrate. And in this regard, we also wanted to preserve the lignin. Lignin is actually electroactive, and the reason for this is that it can switch between the hydroquinone and benzoquinone structure, so it can exchange 2 proton and 2 electron. Furthermore, the sulfonity groups that we introduced during sulfonation can also act both as dopant and stabilizer for the polymer phase. So in the first case, we have wood and pPSS composite. In this case, sulfonation was followed by the infiltration with the prepolymerized pPSS. In this case, the particle size was around 30 nanometers. And we could see the influence of the sulfonation already macroscopically, because if we try to introduce the polymer, which is black in color, into native wood, then we can see that we could not have any polymer within the material. And this is actually a very thin material. It's only 0.75 millimeters. Instead, if we use sulfonated wood, then we could see how the polymer could go through the material without problems. Similarly, from SEM, we could not see any presence of the polymer in the case of native wood, but we could actually spot the polymer as a very thin layer on top of the lumen surface in the case of the sulfonated wood. This is quite difficult to spot, so what we used was critical point drying, which partially solubilizes the polymer to actually peel it off from the wood structure and to observe its morphology. We could first of all see that the polymer is present in all the lumens, which proves the very good infiltration, and that it was laying as a very thin layer on top of the lumen surface. From the longitudinal section, we could also see that the polymer, which looks very different from the directional microfibril in the cell wall, is still deposited as a continuous layer. And a uniform morphology, as well as a continuous layer, it's argued to actually improve the electrochemical properties. And the reason for this is that then the charge can move more easily if the morphology is smoother. So regarding the electrochemical properties, if we see what happens with the native wood infiltrated with pPSS, then we could see actually an improvement of conductivity of 7 times the more we push sulfonation, as well as 3 times in the case of the capacitance. And the reason for this is that the permeability of the wood is higher, so we were able to introduce more conducting polymer. At the same time, as I just said, the coating was uniform inside the material, and this is argued to improve the electrochemical properties. We're also using the charge storage capability of lignin inside the material, which was not removed, and at the same time, the sulfonic groups are used as counterion and dopants for the polymer phase. There is an however, and it is that we've seen that the polymer was confined to the lumen space. However, if we want to make the most of the electroactivity of lignin, that we need to access lignin better. And one possibility to do this is to use smaller molecules. So in this case, we follow sulfonation with in-situ polymerization of pyrrole. So we're using monomers instead of pre-polymerized polymer. And here again, the sulfonation could see to improve already the polymerization after only 3 minutes after the start. And we focus on 2 different sulfonation times, and we can see here again the polymer is black. The sample turned black for the sulfonated one, but they stayed native color in the case of the native wood. And the reason for this is that the sulfonic groups can actually act as a nucleation site during the polymerization phase. So here the sulfonation contribution was visible from the very beginning. Furthermore, and this is something we did not expect, is that the sulfonation also improves the morphology as well. And here we could see how in the native wood, the polymer was deposited as very coarse nanoparticles, and these nanoparticles become smoother and smoother with longer sulfonation time. So actually, and this was presented in literature as well, the sulfonated groups can act as a stabilizer for the polymer phase and improve its solubility. Here again, an improved morphology also means easier electron transfer and improved electrochemical properties. The question remains if, however, we infiltrated the cell wall, which we're trying to achieve. And the answer is yes. And we could see this with the EDX. We mapped nitrogen, as nitrogen is present in polypyrrole, but not in wood. And we can see that there is an increase of the atomic percent of nitrogen the more we push sulfonation. And we could also see a uniform distribution of nitrogen both in the mid-lamellar region as well as throughout the cell wall. How does this, however, affect the electrochemical properties? Here, compared with the composite obtained with the native wood, we could see an improvement of 16 times in the case of conductivity and 8 times in the case of capacitance. The reason for this is, again, the same thing that we've seen before. So we're introducing more polymer inside the structure, using sulfonic groups as counterions, and we're also using the charge storage of lignin. However, in this case, we're using more the lignin. So we're using also the lignin that is present in the cell wall. At the same time, we've seen how the sulfonated groups can act as nucleation site during the polymerization phase, as well as they help to stabilize and solubilize the polymer so that a more homogeneous morphology can be obtained. Here again, there is an however, and it is to permeate the cell wall. In this case, we decided to start with very small molecules, and that in the end, we wanted to polymerize this in situ. However, polymerization must not be always easy, and at the same time, what happens if we want to start, for example, with a pre-polymerized polymer? In this case, then we decided to work with not only wood chemistry, but also wood morphology. So in this case, the sulfonation was followed by directional freezing to achieve what we call wood foam with a much enhanced porosity in the wood cell wall. This was followed by the infiltration of the exact same pre-polymerized pPSS as the previous study. So first of all, what happens during freeze drying? We put the samples with the fiber direction in the vertical one on top of liquid nitrogen. Then we take advantage of what happens during sulfonation, which means that we're swelling the cell wall because of the repulsion of the sulfonic groups within the material. At the same time, the hydrophilic behavior also increases and we have more charged groups inside the structure. So once we put the sample on top of liquid nitrogen, then it's expected that the ice crystal will actually be able to grow along the longitudinal direction. And the more the material is freezes, the longer these crystals grow. Then the crystals are removed by lyophilization, freeze drying of the material, leaving these parallel channels inside the cell wall. How these channels actually look, we can see from SEM. And here we can compare the structure of native wood, so with quite thin and very compact cell wall, compared to the obtained wood foams. Here we see that the cell wall is much thicker, and we have a lot of this porosity, which we define as alveolate structure. So it's an array of deeply pitted cavities of irregular size. And they look a little bit like the structure of bread. The diameter of this material, of this porosity, is around 100 nanometer, which potentially should be bigger enough to host bigger moiety inside the cell wall. The mechanical properties of the material were actually very interesting, as he actually presented the highest specific Young modulus as well as specific compressive strength compared to other foams or aerogel obtained by either cellulosic or wood materials in literature. And the reason for this is both the fact that we are preserving most of the components in the wood, as well as embedding this porosity into the native cell wall structure. So what happens when we try to introduce p.PSS? We could see from Raman spectroscopy, and here p.PSS is represented with the blue color, is that we have the presence of the polymer again in the middle lamella and on the top of the lumen surface, as in the previous studies. But we could also see a lot of dots representing the polymer into the alveolate cell wall structure that we have created, so that we could see that this alveolation is actually bigger enough to host a polymer that in this case was around 30 nanometers in diameter. Furthermore, this material presents very interesting mechanical properties, meaning that it is compressible in the radial direction. These are 100 cycles of compression of the material, and we can see that there is not a lot of loss in strength even after 100 cycles. Furthermore, as this material is conductive, because we introduce p.PSS, then we could also see, if we connect the material to a multimeter and we press it at the same time, that there is a reduction in the resistance output from the material, the more we compress it. So if we, in real time, monitor these resistance while compressing the materials through different cycles, then we can see a output of resistance that is very well modulated, and it's reproducible over the observed time span. So to summarize this part, then we could see that sulfonation for all of this material was very important to activate and put more in contact the wood structure with the conducting polymer. We also achieved very different morphologies with the different studies. We had a thin layer coating the lumen surface in the first case. Then we were able to infiltrate and permeate the cell wall by starting with smaller molecules, while in the last case, we also permeated the cell wall, but instead of using smaller molecules, we actually modified the wood itself, which also showed additional properties such as the compressibility. So to summarize my thesis work, what we could achieve was a better understanding of the structure-property relationship between different wood modification approaches, and that in most of the cases it was fundamental to preserve the structure as well as the component as much as possible, while at the same time increasing both the conformability to densification as well as the electrostatic attraction between the wood structure and the conducting polymer. Furthermore, we could see that if we understand the mechanism of both densification as well as polymer infiltration, then we can actually control it while we go and modify our wood material. Secondly, we could see how important it was to preserve the component, especially lignin, which in the first section was very important to act as a binder for the thin film, while in the second section, it could be used as electroactive material for energy application. Finally, we could also see how different wood modification can broaden the use of wood in functional material. In the very first study, because it was possible to completely delignified wood without it falling apart. And in the very last study, we could see how it's possible to tune the microstructure of the wood cell wall so that it can actually host bigger moieties. To conclude, I already would like to thank a lot of people that have contributed to this work. First of all, both my supervisor, Professor Zhou, and Professor Lash-Berlin, all the collaborators for this work, and both Division of Glycoscience as well as Division of Biocomposite. then the Wallenberg Wood Science Center for the funding and research from the infrastructure. And of course, all of you for being here and listening today. Thank you.